Hey, we're back for more of 621. Decided that example 3 and 4 needed their own videos because they go a little bit deeper than examples 1 and 2, and I wanted you to focus on those at two different times. So here's how we'll begin those two problems. An initial condition determines a particular solution. We know that by requiring that a solution curve pass through a given point. That's your initial condition. So I'll note that here for those of you just catching up. Now, if that curve is continuous, it pins down the whole entire domain. If it's continuous, then you know the whole function from negative infinity to infinity, or at least over its entire domain. But if that curve is discontinuous, so if there's a jump or a gap or an asymptote somewhere in that function's solution, then the initial condition's only going to pin down the continuous piece of the curve that the initial condition point passes through. In that case, you're going to have to give a domain with your particular solution, since that particular solution is only applying to the part of the curve that is continuous. So we're going to see that in example 3 here. Find the particular solution to the differential equation dy dx equals x minus secant squared x with the initial condition that y equals 3 when x is 0. So here's, oops, I thought I was on highlight. Here's the differential equation we're going to solve, and that shouldn't be too tough. What function has a derivative dy dx? Easy, that's y. Let's move to the x. So now, what function has a derivative that is x? So let's go through this with the power rule, but backwards. This is x to the first. So the function who has that derivative is going to have a 2, 1 plus 1, 2 in its exponent. And then when we differentiate x squared, that 2 is going to come to the front as a multiplier. It's going to need to multiply by something to become 1, and it's just its reciprocal. So we're going to put the reciprocal of 2, which is 1/2 in front. Now we move on to minus secant squared. The derivative or the function whose derivative is minus secant squared is minus tangent x. I feel like we did that in the last video. And then we have a plus c. So there's our general solution now to the particular solution using the initial condition that y is 3 when x is 0. So let's see, plug in a 3 for y and let's see, a 0 for x. So 1/2 times 0 squared minus the tangent of 0 plus c. So 1/2 times 0 squared, that's 0. Tangent of 0, also 0. So this means that c is 3. And that means our particular solution is y equals 1/2 x squared minus the tangent of x plus 3. But I'm not going to box it yet. Check out the graph over here to the right. Notice that we have vertical asymptotes at negative pi over 2 and at positive pi over 2. So this function's discontinuous. There are 3, I guess we can call them branches to this function. And since 0, 3 is only going to apply to the portion or to the branch that's kind of in the middle here between negative pi over 2 and pi over 2, that's the only part of the function that this initial condition kind of nails down. So we need to say that this is our particular solution, but right now it only applies to a domain of negative pi over 2 is less than x is less than pi over 2. So that's kind of a stipulation that goes along with your particular solution if indeed this function is not continuous over its entire domain. So here's another like that from your textbook. We want to solve the initial value problem explicitly. So that means we want to find the particular solution. Here's the differential equation. dy dx is equal to negative 1 over x squared minus 3 over x to the fourth plus 12. And your initial condition here, y is 3 when x is 1. So the first thing I'm going to do is a little rewrite. I'm going to call this dy dx is equal to negative x to the negative second minus 3x to the negative fourth plus 12. I think that's going to help me out with my kind of reverse power rule when we find the antiderivative. So now to the solution y equals. I'm going to carry on the negative sign with me. So this is to the negative second. We're going to do the same thing we did on the last one. So x, now this was negative 2. We're going to add 1 to it, So now we're at negative 1. And then the reciprocal of that, so then that's going to be a negative 1 in front. Reciprocal of negative 1 is negative 1. All right, let's move on to the second term. Minus 3. Let's take the x. We're going to add 1 to the negative 4. So now that's negative 3 in front. And then that reciprocal into the front as a coefficient, so negative 1/3 there. Then what has a derivative of 12? 12x, and then our plus c. All right, so let's simplify this up a little bit. Y is equal to negative 1, that's 1. X to the negative first, drop it. So this whole first term is just 1 over x. And then minus 3 times a negative 1/3, that's 1. And then x to the negative third, drop it. So this is plus 1 over x to the third plus a 12x plus c. Now to our initial condition. Replace y with 3, replace x with 1. So let's see, 3 equals 1 over 1 plus 1 over 1 cubed plus 12 times 1 plus c. That's easy enough. 1 over 1 is 1. 1 over 1 cubed is 1. So this is 3 equals 1 plus 1 is 2. 2 plus 12 is 14 plus c. And that means that c is what, minus 11? Because 14 minus 11 is 3. Yeah. So now to our particular solution, it's y equals 1 over x plus 1 over x cubed plus 12x minus 11. But it's pretty clear, I think, from the beginning that 0 is not in the domain of this function. So we have a discontinuity, and you probably know it's a vertical asymptote at x equals 0. So there's a branch to the left of 0, a branch to the right of 0. And if you visualize that, there being a vertical asymptote somehow or another here at 0, and our initial condition is 1, 3, x is 1, y is 3, this only pins down then the right side of the solution. So we're going to have to say this only applies to x greater than 0. And once more, that's only for discontinuous functions that you have to do that. So it is probably worth a little mental check on your questions. Hey, is this a continuous function or no? Yeah, it's got a 0 in the denominator. Yep, that's discontinuous, and give it a little waiver there, or condition that, hey, this only applies to the domain where my initial condition came from. All right, another example for this video. Sometimes we can have a question constructed in such a way that it feels like there's no way we can really do this. But because we have the fundamental theorem of calculus, we do have kind of a unique and interesting way to solve. So here it is. Find a solution to the differential equation. This time it's written as a function. F prime of x is equal to e to the negative x squared, where now we have an initial condition f of 7 equals 3. And this is just another way of saying that y is 3 when x is 7. You probably recognize that already. F of 7, f of x is equal to the x value, so 3. Okay, so we've got an initial condition. We've got a differential equation. If we started this the same way as the other questions, we would just begin by writing, well, f of x is equal to, and then we take the antiderivative, and we've already hit a roadblock, because I can't just find the antiderivative of e to the negative x squared. You can't go adding 1 and putting 1 over that in the coefficient place, because e to the x doesn't behave like polynomials. And if I stick an x in front of here, which I would have to, then now I'm talking about product rule, and we're just out of solutions here. So this isn't going to work, and I need another way to go about this. But let's remember the fundamental theorem of calculus, and then we'll come back to the problem. Fundamental theorem of calculus says something like, if you have an integral of, let's call it f prime this time, of some derivative there from a to b, then this is equal to the antiderivative of that, so f of x, evaluated from b to a. So it's actually equal to f of b minus f of a. Well, interesting, because I have an f prime, And I've also got f of some number. Interesting. And I'm trying to solve the differential equation, which would be in the form of f of x. So maybe in one place I stick a 7 and in the other place I stick an x or something, and it feels like I'm coming up on an answer here. So let's try this out. Let's see if we can fit all of the components and pieces that we have into the fundamental theorem of calculus. It'll go like this. The integral of our derivative, which is e to the negative x squared. Only let's hold off on the x's at this point. Maybe let's call it t, since I know I'm going to have to use an x somewhere else. Let's go with a dummy variable, e to the negative t squared dt. And then let's see, if I'm going to set this up, let's see, I want the 7 in place here. Let's put the 7 down there. We know that we want to have the x in there, so we have an f of x, and all right, that's that. And this is going to be equal to, now by the fundamental theorem of calculus, the antiderivative of this derivative, which is just the function evaluated at x and at 7. So another way to write that is it's f of x minus f of 7. Oh, interesting, because our answer is f of x. And we have that. And we know what f of 7 is even. That's 3. So if we just kind of reorder things here, we have f of x is equal to the integral from 7 to x of e to the negative t squared dt. Then we would add f of 7 to both sides, so plus 3. And while this isn't a very conventional looking function, it is a function. F of x is equal to the integral from 7 to x of e to the negative t squared dt plus 3. And you can actually evaluate this function anywhere you want to. It's more of a TI calculator, a graphing calculator thing. In our calculators, we use int, that numerical integral, in the math menu, and we could evaluate it. It's an answer. So let's see one from the textbook. In this exercise, we want to solve the initial value problem using the fundamental theorem, and it's kind of set up the same way. So here's the derivative. That's going to go into the integral. And the reason I know I'm going to use the FTC here, not just because the directions say to, but because I can't find an antiderivative of the sine of x squared in my head. I'm not even sure I could with upper level calculus. So I'm going to put that into the integral with a dummy variable. Y is 5 when x is 1. So this is just a 1 comma 5 or an f of 1 equals 5 type scenario. So let's give this a shot. The definite integral from 1 to x of the sine of t squared dt. There's your dummy variable since we're using x as a limit of integration. That's going to be equal to the functions. This is the derivative as the integrand, so it's actual antiderivative, the function evaluated at x minus the function evaluated at 1, which then means that f of x is equal to the integral from 1 to x of the sine of t squared dt, and plus f of 1, and since f of 1 is 5, plus 5. There you have your answer for that one. And that's going to end this video so we can finish up with slope fields next. Come back and join me.